In this particular question, we've been asked to find the point on the line y equals negative 2x minus 1 that is closest to the point 1, 2. Well, I'm going to start by creating a very rough sketch of my question. I have a linear function which has a y-intercept of negative 1 and a slope of negative 2. So I've made a rough sketch of that. I also have the point 1, 2, which I've plotted roughly. Now what I want to do is I want to find some point on that linear function such that the distance between that point xy and the point 1, 2 is minimized, or is the smallest possible. I've drawn that in with a little green dotted line. That doesn't necessarily represent the shortest distance on my rough sketch, but I'm just using it for illustration purposes. So what we're trying to do is minimize a distance. Well, let's start with our distance formula that you should have used in your grade 12 mathematics course. D, or distance, is equal to the square root of x2 minus x1 all squared plus y2 minus y1 all squared. Well, we do have one point. We do know that the x-coordinate of one of our points is 1 and the y-coordinate of that same point is 2. So we can substitute into our equation and we get that d is equal to the square root of x minus 1 squared plus y minus 2 all squared. Now, in its present form, this particular equation is not a function. It has three variables in it, d, x, and y. We'd like to change it such that we're only dealing with two variables, and then, in most likelihood, we're dealing with a function. So we know that our y-coordinate on this particular function can be expressed as negative 2x minus 1, because we're dealing with the linear function y equals negative 2x minus 1. So our distance formula now changes so that it reads d equals the square root of x minus 1 squared plus negative 2 minus 1 minus 2, all in brackets, squared. In the next step, all I've done is combine my like terms, and in the step that follows, I've squared both my binomials, and I've used my distributive property to do so. So I end up with d equals the square root of x squared minus 2x plus 1 plus 4x squared plus 12x plus 9. I've combined my like terms, and rather than expressing it as a square root, I've used the exponent 1/2. So I now have d is equal to 5x squared plus 10x plus 10, all in brackets raised to the 1/2. Now I'm going to take the derivative. In this case, I'm going to have to use the chain rule because I have a function within a function. I have a quadratic function embedded within an irrational function. Taking the derivative, I get d prime is equal to 1/2 times, in brackets, 5x squared plus 10x plus 10, all raised to the negative 1/2, times 10x plus 10. I'm going to take that derivative and set it equal to 0, and you'll notice I've expressed it in a slightly different manner, but it's still equivalent to what I had in the previous step. So that I get 0 is equal to, in the numerator, 10x plus 10 divided by, in the denominator we have 2 times, in brackets, 5x squared plus 10x plus 10 raised to the 1/2. Now, what I have to do is take a look at that derivative, d prime, and I have to say, are there values for x for which d prime does not exist? Well, d prime does not exist when the 5x squared plus 10x plus 10 is less than or equal to 0. What you'll notice is that there is no solution to this particular inequality. So there are no values of x for which d prime does not exist. That makes life a little easier for us. Then the other situation we have to consider is, when is d prime equal to 0? Well, d prime is equal to 0 when the numerator, 10x plus 10, is equal to 0. So 0 equals 10x plus 10. I can rearrange quickly and solve for x, and x is equal to negative 1. Now we need to find the corresponding y-coordinate, because all we have right now is the x-coordinate of our point. Well, we know that y is equal to negative 2x minus 1, so y is going to equal negative 2 times negative 1 minus 1, or y is equal to 1. Now, normally we would have to take our second derivative and determine whether this is truly the minimum for our particular function. This second derivative is very difficult to work out. It's long and cumbersome, and we're not going to bother with this particular type of question. You should be able to tell, even based on our answer of negative 1, 1, and our rough sketch, that this does indeed appear to be the closest point on our linear function to our point 1, 2. So we are probably correct with this. If you're not sure, you could always go and graph our function d and confirm that by finding its minimum on that particular curve.